So we have talked about the Newton's law of motion. We talked about the topic about force. So this is really a special topic about force. So it's dealing with the case when the object is at rest. So we call you may call it the topic statics. So that means the study of equilibrium. In the last topic, actually, when you look at this equation, net force equal ma. So you may say that if the net force is zero, then the acceleration is zero. Yeah, that's true. But does it mean that the object is in equilibrium if the net force is zero? Not necessarily. So just have a look at this diagram. So in both of the case, the net force is zero because there are two equal but opposite forces acting on the object. So that means the net force is zero. But obviously, the one on the right hand side will rotate, but the one on the left hand side does not rotate. So that means we need to have one new quantity to deal with the case on the right hand side. So that term we call it the moment, or we call it the torque. Torque is for US. For UK we call it moment. It's not called the acting point, we call it the points of application. The points of application. The moment is the measure of the rotation effect due to the points of application. The position of the point of application. So let's see how we define the moment. So we look at this formula. Look at this book. Because I didn't teach you the cross product yet, so just look at the scalar form. There is a moment equal to RF sine theta. So what is R? R is a position vector pointing from the reference point, or actually you may actually better call it the reference axis or rotation axis, and then to the point of application of the force. Okay. And then theta is the angle between the vector R and F. It's either this one or this one. It's just the same, is it? So the form is like this, okay, RF sine theta. You may ask why there's a sine theta there. And let's consider one case. So that's the door. So you look at it from the top view, Here is the hinge of the door. This is the knob of the door. You know what's knob, is it? So let's say if you, this is your room, this outside your room. So let's say if you want to open the door, so you apply the force at the knob, is it? So let's say if you have opened the door already, okay, so let's say the door is somehow in this angle. So if you push the door in this, if you give the force along the direction of the door, then you notice that the door does not rotate. But if you apply the force at some angle with this direction, the door can still rotate. So do you see? So what happens if the force is parallel to the R? This is the R. If R is parallel to F, then the angle theta is zero, or you may consider it as 180 degrees. It doesn't matter. So sine 0 degree or sine 180 degrees still give you sine theta 0. So that means the torque is 0. Then that means the object does not rotate. Okay. So this gives you some hint, some idea why there is a psi theta. But if we may also rewrite the formula like we multiple R by the psi theta. So what you can see from this diagram is like, so R times the psi theta, then will give you this length. So this is a perpendicular distance from the reference point to this dotted line. This dotted line we call the line of action of the force. It's just the line of the force. You just extend the force to give a line, and then this is the perpendicular distance. So this is R perpendicular, and then times F. So we just consider, we just need to, we just care the perpendicular distance. Sometimes you may also call it the moment arm. Just like similar to when you open the door. So you apply the force at this point instead of this point, because you know at this point it's much easier to open the door. But why? Because you enlarge the moment arm to give a larger moment by considering this formula. Okay. But if you open the door by applying the force along this direction, this force will pass through this point to give the perpendicular distance 0. That means there's no moment. So that means the door does not rotate. Okay, so that's the idea of the moment. So you may also wonder, so why I put a head there? You know the head means it is a vector. So how about the direction of the moment? Right now you need to know that the direction of the moment there's two directions. One direction is a clockwise direction. Another one is an anti-clockwise. Okay. So how do we know the direction of the moment? We just look at the effect of the force. So let's say if you apply the force at this point, then if you let this point to be the reference point to take the moment, okay, you just consider this point is fixed, but the object can rotate about this point. Then when you apply the force at this like this, and then you know that the object will rotate anti-clockwise. Okay? So that's why we say this moment is anti-clockwise. If you apply the force like this and let this to be the reference point, then you know this force will cause the object rotate clockwise. Now whether the moment is clockwise or anti-clockwise, it depends on the direction of the force and also the point you take the moment. It's very important because R depends on the point you take. So let's say there's a rod here. So let's say the rod is 100 cm or 1 meter. So let's say T is 20 cm, the obviously is 80 cm. So let's say you apply a force 5 Newton. If you take the moment at this point, then it counts as a clockwise moment. And then the moment will have the magnitude, that is 5 times 0.2, that's 1, with the unit Newton meter. And then if you take the moment at this point, you consider this point is fixed, and then the object can rotate about this point. Then this moment is a anti-clockwise moment. And then the moment will have the magnitude, that's 5 times 0.8, that's 4 Newton meter. So where should we take the which point we should take the moment? It totally depends on the question. and but most likely if there is a hinge, so just like a door. So let me give you some example. Let me see if there is some example I put it down here. I think no. So let me draw an example here. So let's say here is a wall. So there's a hinge. You know what is a hinge, is it? There's a hinge attached to the wall with a rod at this point. So also a string connected to the rod. In this case, most likely you will take the moment at the hinge. Yeah, because there's a hinge. If there's no hinge, then we can take moment at any point you like. But of course, as some of the points will make the question easier, will make your calculation easier. But some of the point will make your calculation seems impossible. It depends on your experience. Yeah, so I will skip this one 5.2. It doesn't matter. Why oh. So 5.4 is the equilibrium. What is equilibrium? So equilibrium is the state of rest. So it means there's no translation motion and no rotational motion. Translation motion is the object that is only you may just consider it translate along the x-axis, y-axis. That means it's moving to left, right, up or down, and something like that. But the object does not rotate. Then these two are different motion. We can define equilibrium in different ways. So in most of the cases, the question talk about equilibrium. It just means remember this criteria. So remember, in most of the cases, the question is talk about this one, dynamic equilibrium. In this case, the object can still move with constant velocity or rotate with the constant angular velocity. So what is dynamic equilibrium? When the net force is zero and also the net moment is zero, then the object will be in dynamic equilibrium. Now you may ask, okay, so at which point we should take a moment? And at which point the moment should be zero? It is really a complicated case. Let me try to find some white space. I think there's let me remember so let's use some. So let's use this white space here. So you may copy it down by yourself, okay? So dynamic equilibrium. Dynamic. So the object is in dynamic equilibrium if and only if, okay? So we can either say the net force is zero, and the net moment is zero at any point. So you need to make sure that the net moment is zero, whatever the point you take the moment. You may also ask, what does mean by the net moment is zero? So in other words, okay, the net moment is zero. It means that the total clockwise moment equal to total anti-clockwise moment. I'll give you some example later on. Okay, but actually, we can this condition are too strict. So then how this actually is a equivalent form. So we can say the net force is 0 and the net moment is 0 at one arbitrary point. So you don't need to take moment, you don't need to consider the moment at any point, just take the moment at one point and to see that whether the net moment is 0 or not. And also, okay, you can, this is also equivalent to it, the net force is 0 at any point. If the net moment is 0 at any point, it implies that, or you may say it already includes that the net force is 0. But I'm not going to prove it. It's a bit complicated to prove it. So in most of the case in exam, in a commission or in any exam, I will just choose the second one. Okay, we just take the moment at one specific point, and then to also see whether the net force is 0. If yes, then the object is in dynamic equilibrium. Okay, so let's give you one very simple example. So just okay, so let's say this rod is in equilibrium. So may you can you tell me which guy is fatter, A or B? I think all of you should get the correct answer, is it? A should be fatter. So how can we prove it? So let's have a look at the three-point diagram of this rod. So there is the rod is in contact with this pivot. So when two objects are in contact, so there should be a normal action. Let me just call it N. A and B are at rest on the rod. So the force acting on the rod by A is equal to the weight of the object. But this force is not the weight, okay? So this is a force when the A is in contact with the rod. So this is also the normal version. But because the A is at rest, so that means this force should have the same magnitude as the weight of A. So this MAG, mass times G is the weight. So this is the MBG. So if you consider the net force is 0, okay, then because all the forces are vertical, so you will say the total upward vertical force equal to the sum of the total downward vertical force. Okay, I think it should not be difficult for you to write down this formula. So this is for the net force equal to 0. And then if we will take the moment at any point, so let's say, let me take at this point, okay? So let this distance to be R A and R B. And then if the take moment at this point, so there are three forces acting on this object. Then you need to consider all the moments of these three forces. But if you can see that the N passes through this point, passes through the point you take the moment, that means the perpendicular distance is 0. Then the moment of the N about this point will be 0. Okay. The moment of the MAG about this point is a anti-clockwise moment because uh yeah, and then the moment of the MBG is a clockwise moment. You see it? Then we say that because all the rod is in equilibrium, then the net moment is zero. So that means a total clockwise moment. Clockwise moment is MBG times the distance RB. Then that equal to the force MAG times the perpendicular distance RA. You can cancel out the G, and then obviously you can see that because RA is smaller than RB, so therefore MA is larger than MB. Okay. You may also wonder, okay, if how about if I didn't take the moment at this point? Yeah, you may also take the moment at this point. I saw. Let's say this point, okay. Then at this point, the force MAG passes through this point, and there's no moment of the force MAG. And then the big N is a anti-clockwise moment, so N times RA. Then that equal to the clockwise moment provided by the force MBG. But the distance here is RA plus RB because it's a distance from the force MBG to the point. Now, you may try to now you can try Now what you can try that is you substitute the n in this formula. Then you can after you simplify it, and then you will get this formula. Okay. So that can show what I mean by the above free equilibrium conditions. But if you don't understand, then just leave it. Any question? Maybe I give you 1 minute to digest it. Okay, then let's move on. Before we go on to talk about the question, so there are 3 different types of equilibrium. If you classify in by stability, the first one is stable equilibrium, unstable, and neutral equilibrium. I think you can understand it by just looking at diagrams. Is it? So when this object is displaced by a small displacement, and it can still return to its original position. So that is the stable. This is a stable equilibrium. Okay. Unstable and then neutral, and that's it. If you want an object to be more stable, you need to lower the center of mass. We'll talk about this later on. If you want to, So if you like, we may go to talk about some simple example first before we go on to talk about these Olympic questions. Okay. So I open a Word file. So just use example, just I just taught. So consider there's a rod, okay? It's attached to the wall by a hinge. And there's also a string. And the rod is also connected by a string. Just draw the diagram, okay? And then you understand it, that's fine. Shit. So I'm not connecting the string to the middle. Let's say I connected the string to the middle point. Oh no, it will be too easy. You see, let's say 4/3, okay. So let's say the rod is 2 meter long, and this is 0.5 meter. So let's say the rod has the weight, the mass is 2 kg. Okay. So what I want you to do is, so first of all, draw the three-point diagram. So may you draw it on a piece of paper and then just send me a photo on the WhatsApp. Okay. And then next step we want to do is find the tension. And then next step we want to find the force acting on the rod by the hinge. Okay, so that's all we want to find. So and then I'll let this angle to be, let's say 30 degrees. Okay. So you just do the part A first, because if you can't do the part A, then then you can't do the part B and part C. So I give you 2 minutes. You draw it on a piece of paper and then send it to me. Just take a photo and send it to me in WhatsApp. So the three-point diagram of the rod, actually there are three forces acting on the rod. So first of all, there's the weight of the rod. This mass times m times g. There's a tension acting on the rod. So this is 30 degree. And also don't forget that the rod is hinged. So that means at the hinge, there should be also a force. So you may ask, what direction is the force acting at the hinge? We don't know, but you may need to think about it. So first of all, if you look at the horizontal forces, so only the tension is has a horizontal component. So that means there should be also a horizontal force acting on the rod by the hinge to the right to compensate the horizontal component of the tension, that which is to the left. So you should have a one to the right to cancel each other. But don't forget that there there may be also a vertical force at the hinge. So hinge is a really very annoying part in the question, because we can't tell what direction of the force is there at the hinge. So it's better for you to let the two forces at the hinge, one is vertical and one is horizontal. So for the horizontal one, you can analyze that it should be to the right, because to compensate to the left component of the tension. And then for the vertical component, so if you don't know about it, okay, it's fine for you to. So let's say if you you take it to be vertically downwards. So let me label these two as N1 and N2. Okay. So how can we find the tension? Do you still remember? If there's a hinge, most likely you take the moment at the hinge. So you take the moment at this point. N1 and N2 passes through this point. So there's no moment given provided by N1 and N2. And then, so the weight will provide a clockwise moment. The tension will provide an anti-clockwise moment. So that is T psi. So anti-clockwise moment, okay? Remember RF psi theta, also multiplied by the distance, is 1.5, equal to the RF. So you may have a look at this formula to see if you have any questions. And what you do next is just use your calculator. Okay? I'm just lazy, use my calculator. So you get 26.16 Newton, is it? So that's the force, the tension force. Okay, so how about the force acting on the rod by the hinge? Now, so this one, this is the rod is in equilibrium. So that means the condition of the net moment is 0 and the net force is 0 are both satisfied. So we have considered net moment to be 0 in the part B. Then for the part C, we consider net force is 0. So look at the horizontal force. So that's M1 should be equal to T cosine 30 degree. Right? So this one you consider the horizontal component. Then for the vertical component, so T has a vertical component that is upwards. N2 and the weight are downwards. So that means T sine 30 degrees should equal to N2 plus 2 times 9.81. So let's see what you get for N2. Using a calculator, you get negative 6.54. So what does it mean? What is negative? It means that this force should be vertical upwards instead of downwards. So it should not be negative. It should be vertical upwards. It should be positive. So it should be upwards 6.54. It doesn't matter whether you let the force in the correct direction or not. But of course, it's better for you to, if you know the direction, it's better for you to let it to be that direction. But if you let it in the opposite direction, you get the negative value. But don't worry about it. That means it's in the opposite direction. Okay. So that is a simple example for the moment. Okay. I'll just capture the screen here and then send it to the WhatsApp. If okay, now, so I send you this textbook. So may you have a look at from this page to the end of this topic. So that means to up to this page. We are up to 129. So yeah, although these are really tough questions, but you may have a you may prepare for the question first. You may have a look first, and then you may have a better understanding in the next lesson. I also send you some other simple, easier DSC exercise with solution first, okay? Then you also have a look at the exercise about the force and also the moment. So let's say some time for next lesson on. I really have a busy week. So I need to take a rest. So let's meet you on Saturday, okay? Saturday, and I'll send you the exercise now, and then you have a look at it, and then I'll upload the video soon. Today.